So, where was I? Right. So I will cover roughly 4 parts, which correspond, I guess, broadly to some different areas of my work related to ontologies over the years. I will start with chemistry. Chemistry is a really fun topic to ontologize. And then I will spend some time talking about energy systems. So this was a project alluded to by Fabian yesterday in his talk, and another topic which has many challenging problems for ontologies. And then I will talk about mental functioning, emotions, and so on, and behavior. And these are projects which have been consuming much of my time for the last nearly decade now, I guess. And then finally, I will indulge a little bit of speculation or discussion about ontologies in the context of AI and what's happening in technology at the moment, which I think is also quite interesting. So, chemistry. So as Barry mentioned, the project which I was involved in when I first became an ontologist, accidentally, was the Chemical Entities of Biological Interest project. And this is a database and ontology, large-scale ontology. It's actually bigger than the gene ontology in terms of content or size of the content, which is being developed at the European Bioinformatics Institute for, I guess, nearly 20 years now. And this is their front page. Every month they provided an entity of the month, so you learn a little bit about a chemical which has been in the news or being topical for one or another reason. And it includes a classification of types of chemicals, so every kind of chemical that is relevant or interesting for something to do with biology. Caffeine is my favorite chemical. I used to say caffeine is my favorite drug, and I really like drugs like caffeine, but now I probably shouldn't say this anymore. So, and it contains this classification of chemical classes, such as purine alkaloid. These are just classes that chemists find. It definitely stops every few Does this one work? No? Hello? Okay. So it's a bit disconcerting if it stops working. Anyway, so these are the types of classes that are in heavy groups of chemicals. There are also a classification of what chemicals do, why they're interesting biologically, and there are representations of the structures of molecules and all sorts of information about them, like their mass and charge and this kind of thing. So when I started on Chemi, it was broadly speaking a classification, but maybe not a fully sort of structured ontology yet. And in the early days also of the Ogo Foundry, there was a community, and one of the first impacts that this community had on the Chemi project was to suggest, and indeed we implemented, making a strong distinction between the classification of chemical entities as independent continuants or as entities that stand in their own right, and the classification of dependent continuants or properties, attributes that chemicals have. In the case of Chemi, this was the classification of what they called roles, which encompassed the biological activities that chemicals have in biological systems, as well as applications, like things that they are licensed to be used for. And making these disjoints was a tricky exercise because they had been, and to some extent kind of still are, a little bit crossing over. And this crossing over relates to how sometimes chemists refer to classes that have some element of both, or refer to classes which are defined based on some sort of use or purpose, such as antidepressant, but also some structural features or so on, and they're talking about the actual molecules and not the attribute of the molecules, not the properties of the molecules. They're just talking about, here are some molecules, and these molecules are antidepressant molecules, right? So the distinction in the language of chemistry was quite a vague one, and as a result, the ontology was quite vague, but then BFO and more, let's say, structured thinking met the ontology, and we figured out a way to make these separations, and we made a kind of principle by which you dealt with these crossover classes, and in the end, the ontology was neater, and it was easier to use it for certain sorts of reasoning tasks where you really needed to know whether you were talking about an activity in a biological context of a chemical or the chemical itself as a molecular entity. So I think this was a really positive impact that BFO and the Oberfoundry had on the chemical classification. We never managed, and I think it's not even desirable, to make a single parent classification hierarchy for chemistry. So chemical classes have this feature that they are kind of compositional in some sense, that each chemical class, each broader grouping of chemical entities refers to some feature that the molecule may have, and these features can then be combined, and as a result, sort of if you go down the hierarchy towards the individual molecules, you are composing multiple features which, higher up in the hierarchy, each of those features corresponds to a class in its own right. So this is what you see here. You see a class like hydroxides, which is a lower level classification of molecular entities, has many parents. On the one hand, it's a hydrogen containing molecular entity. On the other hand, it's a heteroatomic, so it has many different atomic parts. And it's an oxygen containing molecular entity, and so on. And this creates a kind of diamond-shaped classification hierarchy. As you get to the top, in the most general, you have classes like chemical entity beneath which everything else is classified. At the bottom, you have individual molecules, which have many features. And in the middle, you have a vast range of parent classes into which those molecules could be classified and are classified. And choosing one parent out of these examples of multiple parents just doesn't really make sense. So chemistry, I think, and maybe several other domains where the classification is based on features or parts of the overall thing, doesn't really work with this single assertive parent principle. And the domain experts would not accept that. One interesting challenge of language was that we found out that chemists referred quite easily to chemical entities by features of their molecular structures, where molecular structure is the kind of arrangement of atoms and bonds. And if you think about a structure in the same sense as a shape or a configuration, then a structure seems to be a dependent continuum, a quality. But this quality of how the atoms are arranged or whatever is also everything there is to know about the definition of the class of molecules of molecular entities. So the molecular structure and the sort of classification of the chemicals themselves were confused, and people were referring to sort of both of these things. Oh, it's a class of chemicals. No, it's a class of chemical structures, right? And you can imagine how this then creates strange-looking assertions. So when we were starting with chemi, you could infer, because molecular structure was the root of the classification, that a class of chemicals such as caffeine is a molecular structure, but that, if you think about it, doesn't seem right. So we changed the root to be chemical entity, but this doesn't completely resolve the problem. So chemists still refer to molecular structures and interchangeably the classes that are defined by those chemical structures. So it's something which still, in some sense, persists in the language that's used in the chemical domain. And the representation of molecular structures or chemical structures adds another layer, right? So now you have the molecule, the class of molecules, you have the quality of how those atoms are arranged in order to define that class of molecules, and you have representations such as the illustration which is being shown down there at the bottom. Sorry, that's quite hard to see from the back, right? I see people peering over. I hope I haven't used the bottom of the screen too much. So, and this is like three different, somewhat conflated ways of talking about classes of chemical entities. And these are, I think, although they're not conflated in Kebi, and we tried to clean up the way that Kebi works with regard to these things, they're still conflated in the literature, in the chemical publications, in the way that people talk about classes of chemicals. And yeah, I think this is let's say, an ongoing challenge. Another aspect which I must admit is not terribly relevant to day-to-day life, but still quite fun to think about, is the fact that the representation language in which you define new classes of chemical entities by representing the structures that those new classes of chemical entities would have allows you to specify classes of chemical entities that won't necessarily exist. Now in this case, this cannot exist, and this is obvious, so this is just for fun. I think this was some sort of April Fool's exam problem that I found an example of on the internet, but the many examples are much less obvious, where you could have a representation which looks like a chemical structure defining a class of chemicals, and either it contingently does not exist because nobody has synthesized it yet, or it necessarily could not exist, although there are mostly some sort of validations on the software that allows you to draw these kind of structures. But nevertheless, some strange cases may slip through. And in this case, you have a representation which is of nothing. And that's okay, except when you need to kind of use chemical information in a sensible fashion, you need to be able to tell which is representing and which is not representing, and we don't have a good way. And there are lots of databases that do include fictional or arbitrary or not yet synthesized molecular entities in their content. Kebi does have a rule that they do not, so they do not include chemicals in the classification, and this rule comes from the influence of BFO and the Overfoundry community, but it also just makes sense because the vast space of not yet or not created chemicals is infinitely huger than the space of actually existing chemicals, and time and resources are limited, so you want to focus on what actually matters. Another challenge with the Kebi classification, which causes problems for users of Kebi, regular problems for users of Kebi, is this distinction between parts and wholes as it's represented. So even in, I think, in general chemistry, it's quite common to talk about parts of molecules, and they have this expression groups, and groups are parts of a molecule with an explicit attachment point. So you see here, again at the bottom, I'm sorry for people at the back, an explicit attachment point represented in the structure. And what that is trying to say is, this is a part of a molecule attached to something else. And this seems to correspond to the fiat object part in the BFO sense. So you're talking about a part and not a whole. And on the other hand, you have these classes of chemical entities which are defined based on the fact that they are standalone whole chemical entities. But what causes problems for the users is that in many cases these seem to be more or less exactly the same thing, and this is never clearer than in the case of atoms. So in Kebi, an atom is the type of thing that is a part of a molecule. And then you have monoatomic molecules. So whole entities, I think molecule is not the right word necessarily, but whole things which consist of only one atom, right? But this is essentially the same thing. It's just different whether the atom is a part of something else or could be a part of something else or is being viewed as a part of something else. So this is a challenge, the kind of need to distinguish when it seems that parthood is in this case, or at least in some cases, a contingent on circumstances, and not an intrinsic necessary defining feature of the thing itself, right? An atom is the same thing, an atom, whether it's part of something else or just standing by itself. So, yeah, this, it still exists. Kebi still makes this distinction, and I don't know what the solution would be. So another thing which we did then was to look at, so as I mentioned, Kebi has this classification of molecular entities based on the features of their composition, or really how they are made up. But it also has this biological classification, or not only biological, but the classification of what chemicals do, why we're interested in them. And one of the things which we did, and this was, I think, quite a neat finding, was we went through all of them. This was back in 2010, so it's probably changed a bit since then. But we found that it was quite easy, for the most part, to assign the ways that chemicals were used to one of the three different types of BFO's realizable entity. So basic chemical roles such as solvents seem to map quite naturally onto the definition of disposition, in the sense that these were intrinsic features which those sorts of molecules had because of their structure, and that was it. And then there were whole categories, especially because the topic was chemical entities of biological interest. There were large groups of biologically interesting actions which got there in a way because those molecules either had evolved somehow to have those functions interacting with biological systems, or specifically being selected because they had been determined that they had those functions interacting with biological systems. So that seemed to map onto BFO's sense of function. The focus on evolving or being selected so that that class of chemicals has come into existence in a way because of its function, its interaction with the biological system. And then there were things that related to the human world, so things that classes of use of chemicals which were regulated or which related to applications that required a whole social infrastructure in order to be used. And these, they seemed to be socially or externally grounded. So these we mapped onto BFO's roles. And here, I think, again, coming back to language, so the root of this part of the hierarchy of Kebi is called role. And this was very confusing and continues to be confusing because people who know BFO think that the whole classification is a BFO role, but actually it isn't. Some of the things are low-level dispositions, some of the things there are functions, and only some of them, the applications, are what you would consider a BFO role. So the root of this part of the classification should be called realizable entity if it were mapped onto BFO properly. But the chemists and everybody else who ever entered the room in this discussion just wouldn't agree to that. They were like, no, they just couldn't see how this word related to them. The term realizable entity was too foreign for them. So they preferred to stick with role, and as a result, yeah, the language is still ambiguous depending on which perspective or background you have. Another thing that we never quite succeeded is in fully separating these three categories, although they are clear and you can more or less assign them. In some cases, they seem to overlap slightly in the sense that the chemists were not confident in making rigid distinctions between what was a biological role and what was an application. And these are cases where, for example, a particular application has been created out of what is an underlying biological disposition, function, capability. And similarly between chemical roles and biological roles. So here we have polyhierarchy again. But whereas in the case of the polyhierarchy in the structure-based classification, I think here probably it could be potentially resolved with some rules, but I didn't succeed in while I was there. Right, so much for chemistry. Now I will switch and talk a little bit about a different project. So this project is a large energy systems analysis ontology project, which Fabian mentioned yesterday. I was only involved in this project for a short time, I guess, around 2 years or so, and it both pre-existed before I joined it and continues to evolve after I left it. But nevertheless, I think it makes a really good example of some of the sort of puzzles that one can encounter when applying DFO to domain ontologies. I should also say that it was not me who brought BFO to this particular project, it was Fabian. And there are other ontologies in the broader energy and physical sciences communities that have not had BFO's positive influence, and these overwhelmingly tend to be very muddled. So it's a very difficult domain to work with, and lots of really hard puzzles. And even though I will now present some of the challenges associated, just to bear in mind that this is a really good ontology in this domain. So I don't go into the details of this, but this is just a small selection of some of the content to give you an idea of the coverage that you have, specifically dependent continuance, independent continuance, generically dependent continuance, processes, the whole Kahoot, every different part of BFO is represented. The topics that the ontology includes, on the one hand, it's a lot about representation of possible scenarios for modeling and for the way that energy possibilities are evaluated, which tends to be computational simulation. So we have all of these information artifact type of content, simulations, assumptions, scenarios, the software on which these things run, inputs and outputs of data items, and so on. And then you have the whole world, which these scenarios and models and efforts to understand energy use and project energy use into the future, you have the whole world that these things are about. So you have social and economic entities. How much does energy cost? What happens if we increase the cost of this type of energy? What happens if we move this input to that other input? What happens if you can't, in Europe, buy Russian gas anymore, right? These were all important questions. And then you have the whole of the kind of physics part of reality that you have to represent here. You have energy itself, portions of fuel, portions of matter, and their transformations. And of course you have the various devices and artifacts that are being invented. And this is a small picture showing the architecture of the ontology, and you see BFO at the top right as kind of the first import, and all the others derived from it. It also reuses lots of other familiar BFO-related ontologies, such as the information artifact ontology, relation ontology, etc. So one of the first challenges that we encountered in this domain was the kind of, I think, perhaps very familiar to all of the ontology developers in the room, challenge that sometimes the thing you want to talk about, code up about, exchange information about, is some sort of number. Often it's the result of a calculation, or maybe it's a measurement or something, but this is the thing, and the thing is a number. So where do you put it? So the open energy ontology has this concept of quantity value. I think it's not too dissimilar from what OB has, which is then classified as an information content entity, so beneath the generically dependent continuant branch. And this is unsatisfying because the point of the entities that are classified beneath this branch, the quantity values, is that they are numeric and not necessarily that they are information, right? So you have examples like gross domestic product, or power density, or efficiency, and these are attributes that things in the world actually have, right? So a GDP tells you something about what has happened in a country, in a lot of real things, and it's, yeah. There's a sense in which this way of handling a whole part of the representation of the complex world is unsatisfying because you want to talk about what it actually means to be efficient, to be an efficiency, right? And not just the fact that you have calculated a number. But anyway, this is the compromise. We have these quantity values, and they are, whenever there's some or other calculation involved, it automatically puts things into this branch of the ontology. Another challenge, which should be familiar to many potentially in the room, is the challenge of defining organizations. So organizations are peculiar sorts of entities. They appear to be socially constructed and constituted, but they sort of outlive the people who make them. They may continue to exist even if all their members have left, and they may have no physical bearer in the sense of buildings or anything else, right? And then you have the additional need. You need to represent organizations having roles, because organizations participate in transactions and are assigned all sorts of roles in the context of the social world. So you have a situation where you have something which behaves like an independent continuant, but doesn't appear to have anything to constitute its independent existence. And different ontologies have solved this problem in different ways. So in the OEO, an organization is defined as an immaterial entity, which is clearly not the right place, right, obviously, but on the other hand, there is no better place. In OB, organization is defined as a material entity, but with a big disclaimer saying that this was that no consensus was reached on the classification of organizations and whether they were material entities or dependent continuants. And actually, I think it would be really nice if some of the social ontologists in the room could come up with one way for this problem to be solved, and then everybody can just use it. What was that? Sorry?
I said the non-social ontologists will never have it.
The non-social ontologists will never have what? The solution.
Yeah, there's already too much specific.
Never say never. Never say never. I think disagreements can often be resolved. Maybe not always, but I'm picking hard problems here, right? So a little bit conscious. So being the energy, open energy ontology, and having as its topic energy systems and the representation thereof, of course the question comes up, how do you classify energies? And this, as you can imagine, is quite a challenging one as well. So energy seems to be, on the one hand, analogous to something like temperature. And as such, it seems to be a quality of a material entity, right? A material entity has energy in some sort of important sense, and cannot, it has to sort of, something has to change for it to have less or different energy. So in the OEO, energy is defined as a quality of a material entity that manifests as a capability to perform work. But capacity to perform work. But the capacity to perform work, this sounds kind of dispositional, right? You're sort of talking about some future-oriented realization in which work has happened, and you're not talking about something which is present in full at the moment. So in that sense, there's some kind of dispositional element. There's also the problem that as a dependent continuant or as a quality, energy should have always a bearer, but some energy doesn't seem to have a bearer, right? So some energy seems to be its own bearer. So photons aren't that material, right? And the OEO has solved this problem by making a photon a material entity, but that doesn't seem quite right. And you have problems like electromagnetic fields where you have dispositions and energy and action, but it's at a distance and far beyond its bearer, potential bearer. So I would say that this caused many long debates, but on the bottom line is that most would agree that even though this is a very difficult topic, most would agree that energy should be represented as a dependent continuant in BFO terms. But I think the existing representation is still unsatisfying, imperfect. So then there's the additional challenge that if you accept that it should be represented as a dependent continuant, you run immediately into the problem that one of the most important things about energy in the context of energy systems representation is that it can be bought and sold. And that makes it a commodity, and a commodity is a role. And it's not the bearer that's being bought and sold. It just isn't. So energy is moving, and energy is what is being bought and sold. And this means that you have a situation where you have a dependent continuant which is somehow the bearer, or needs to be somehow the bearer of another dependent continuant. And this is not that dissimilar to the situation which Alan was talking about yesterday, where you have generically dependent continuants which, such as software, which is bearing roles. And another example, I think, is software can also be bought and sold. So in some sense, software is also a commodity, and some other examples were mentioned yesterday. So this is not possible at the moment in BFO.
Yes. You can have specific dependence on specific dependence in 2020.
Ah. So, okay. Okay, so. And not generic, why not?
Well, you know, these discussions, how they go. It's coming.
Okay, so this good. This one then is maybe a little bit closer to being possible. So much for energy and its challenges and problems. I think there would be more to discuss, but we have limited time. So now I will talk a little bit about mental functioning and behavior. So this seems like quite a different topic. It's also having a long history. So I started working on mental functioning and behavior in the context of a research stay in Geneva back in 2011, or maybe even, I guess early 2011, 2012, thereabouts. And the challenge was to represent this complex world of the mental, the sort of things that happen in our conscious minds within the broad umbrella of the BFO. And this was, I think, at its time probably quite revolutionary. The whole of representation in the world of psychology was very confusing and not yet, I think they were having, and still to some extent, not yet really seeing the value of standardization and categorization and clear representation such as we have in ontologies, but that's changing now quite rapidly. So this is an illustration of the sort of basic upper level of the mental functioning ontology. We had identified all kind of different things like processes, mental processes, various dispositions, and independent continuum, obviously everything related to the organism, to the human being, that is the main independent entity. Emotions were challenged because of the complexity of the various sub-processes that are related to the overall process. So emotions are even, they have several parts and components, and these seem to be process parts and components, and not material parts or components. So this was also something which was challenging and very interesting to work with. And all of this work was done in consultation with researchers and people who were working in these fields as psychologists, as neuroscientists, as experimentalists. And this was a very interesting dialogue with people who had maybe only implicit sort of schemas or understandings of these core concepts, and then they had to take those implicit and in conversation in order to map out which were dispositions, which were the processes, which were representations, and so on, to sort of gain an understanding of what the domain scientists actually thought in a way that they hadn't asked themselves those questions before. And I think this is still very much an ongoing process. So the emotion ontology and the mental functioning ontology have been living ontologies for now more than a decade, so they are somewhat occasionally updated if there are requests or any kind of feedback and so on, but they're not under massively active development except in the context of the behavior projects, which I will mention in a second. So one challenge which arises from this domain is the very peculiar state of the very peculiar nature of mental processes being conscious, and what this means when you try and represent it in an ontology. And I think here there probably again are no really good solutions, but maybe some comments or suggestions from the audience. So one aspect is that consciousness itself seems to be somehow a part of mental processes, which is completely inseparable, but yet not the full, not everything there is to say about mental processes. So you have some idea of a process part that's going on here. The mental process is a big and complex thing, and consciousness is one layer of that big and complex thing. A lot of people, especially even philosophers, even domain scientists, they like to talk about consciousness as a quality of a process, right? Mental processes have the quality of being conscious. Now this doesn't work in BFO. At the time that we were working with the BFO version of that time, there were process profiles. So we stuck consciousness in process profile, even though it's not either a good fit based on the canonical use of process profile being more for sort of rates and changes in some quantitative value. Something like a fierce process part might also work there, but it's still somehow unsatisfying, because what the domain experts would want to see is something that really foregrounds the quality-like nature of this very important part of the mental processes. And then there were some other aspects which were quite difficult to pin down in terms of the ontological representation, one of which is the fact that you have reflexive relationships. So consciousness creates a subjective perspective, that's your subjective perspective, right? Each person who is having the mental processes is aware in some sense of them. This is they are experienced. So this seems to be a very special type of participation relationship, right? And we don't have, I think, a vocabulary for that. And then there's the fact that there's the whole representational aspect of it, right? If you see something, then you are, somehow your mental process is representing the thing that you're seeing. And this representation is similar but not identical with the kind of representation of a information content entity, right? A generically dependent entity. So these are puzzles for the ontology of mental functioning, which we have some kind of representation, but it's, I think a lot of work could still iron out some better strategies there. So now I want to talk about, for the last part of this presentation, I want to talk more about the Human Behavior Change Project and various aspects related to that. So the Human Behavior Change Project was a big collaborative award funded by the Wellcome Trust to try and solve the problem for the domain of behavior change, of the fact that too many studies are published and nobody can keep on top of the enormous growing literature. I really love this picture. It comes from a opinion article published in Nature, which was something like, you need a constantly updated evidence synthesis or an evidence overview, but you have this kind of monster of papers which is running away from everybody who's trying to catch a grip on it. So the Human Behavior Change Project aimed to provide a structure to the domain of studies of what changes behavior. And I will talk in a minute about what that means, but just from an ontology point of view, this meant that the scope was really broad because the scope is studies of interventions that aim to change behavior, and that can really be many different types of interventions, from environmental changes to individual changes, from pharmacological interventions to counseling or whatever. And then the whole way in which those interventions are delivered, to whom, in which group, and how you compare one part of a scenario, of a study to another part in order to decide what was effective or not. So this creates quite a broad scope for the ontology, and as a result, the combined sort of each branch of this overall ontology having each several hundreds of classes, so the overall project is quite a big ontology. This is the upper level. You probably can't read it, but just to give you a very brief idea, on the left-hand side in red, you have things relating to the study part of the picture. So you are sort of taking one branch and comparing it to another branch, sometimes many branches, and then you're doing calculations such as what is the effect once you subtracted your control group, what is your outcome, and so on. And on the right-hand side, you have this scenario of behavior change, which is not only your intervention, but also the population, the context, the setting, the whole scenario where this thing took place, as well as the intervention and its content. So at the heart of this idea of behavior change is the what's called the COM-B model of behavior. And this is a representation, this is a model which is being developed by my collaborators who are based at UCL. And I mention it just to highlight the central importance of capabilities in this model. So here you have, it's basically a model that says capability, which means what the person can do, combined with motivation, what the person wants to do, and opportunity, what the sort of world allows, or what possibilities the person has, work together to ultimately create behavior, right? So a given situation, in order to, if you have a desirable behavior and an undesirable behavior, you may influence, if you want to promote the desirable behavior or reduce the undesirable behavior, you may need to shift one of these things, make the person more capable, make the person more motivated, or change their environment in order to create more opportunities. And not just to focus on one aspect of this, but really to create a whole picture of what the main determinants of behavior are. And here I think this view of what capability is a very individual human sort of centered view of capability, which maps nicely on, and indeed in the behavior change intervention ontology, we have classified this as a disposition, a personal disposition, a disposition of an individual human. Behavior itself, as well as motivation, these are classified as processes. So motivations are processes in this particular interpretation. And then opportunities are something like an environmental disposition. What does the world allow you to do? So somebody who wants to stop smoking may not have so much capability not to smoke, but if they're in a locked room and there are no cigarettes there, then they have no opportunity to smoke, right? It's just the motivation might be through the roof, but they don't have an opportunity. So you can change people's behavior just by changing the environment. You can also change people's behavior through motivation or through giving them additional capabilities. And here motivation is really a kind of key, important concept, but yeah, capability is very important as well. So one of the challenges which we had and continue to have is that it seems to be necessary in order to define behavior, not just any process that a human engages in is considered behavior. So there are all sorts of processes that a human engages in which are not behavior, such as digestion. This is not considered a behavior according to behavioral scientists. And the distinction between the processes that do count as behaviors and the processes that don't count as behaviors seems to be difficult to pick out without referring to which muscles are involved, and that's very unsatisfying. So if anybody has a better suggestion there, I would be glad to hear it. This is an example, just a subset of some of the different types of behavior classified in the behavior part of the overall behavior change intervention ontology. So you have things like reading behavior, lying down, standing, sitting, whatever, things you would expect. A challenge here is that in order to stick with the true path rule that every instance of a classification at a lower level of this ontology is also an instance of a classification at a higher part of this ontology, it's actually quite tricky to make a deep classification because behaviors, depending on the context, may or may not be. So walking might be for health or for getting from one place to another, or some automatic, like sleepwalking, right? You're not even trying to do it. So it's really challenging to figure out classes that work in the mid-level of this hierarchy, which are always true of the lower level of the hierarchy. Another challenge is the concept of behavior change itself. This is very central. It is the behavior change intervention ontology. Interventions aim to change behavior, but that doesn't mean what you think. It doesn't mean that there is some behavior and after you do the intervention, there is different behavior. It means something like, after you have the intervention, what the outcome is different to what would have been the case if you didn't have the intervention, right? So an intervention that has as its outcome that people who don't smoke don't start smoking, zero change in actual behavior, right? Nevertheless, this can still count as an intervention that has succeeded in changing behavior. Population level interventions do this all the time. So this is quite a perplexing sense of what change means, and defining this in a good way and a BFO consistent way would be really a positive contribution if anybody has ideas. So behavior change here is change with respect to what would have been the case in some counterfactual sense if you didn't have some or other intervention which is been applied. Behavior change in this sense is also then linked to what's called a mechanism of action. The mechanism of action is the action of the intervention in changing behavior from what would have been the case if you hadn't had that intervention. But here in the mechanism of action ontology, you see actually many things which in a way are reused from other ontologies such as the mental functioning ontology and the emotional ontology, because what you see here is a kind of theory of how humans work. So what changes behavior? People might learn something, people might remember something, they might have some social reason for changing their behavior and so on. So the mechanisms of action here are kind of general theory of human internal and external functioning and all kind of relevant aspects. Another challenge is the need to define, so behavior in this sense is often about repeated behaviors over time. So smoking is not about individually taking one cigarette or whatever, but about weeks, months, years of repeating the behavior of having a cigarette. So we needed to come up with some strategy to define these patterns of behavior that repeat over time. And we came up with we defined them in terms of process aggregates, but the challenge here is still that then you're defining a process aggregate in terms of repetitions of a type of behavior, which is a little bit of a peculiar thing to do. So you're talking about smoking, different instances of smoking behavior being repeated over time by the same individual. And then again, as soon as you start talking about complex patterns of behavior over time, you need to define things like frequency, duration, intensity, etc., regularity, all of which are attributes of processes in some sense. And this BFO doesn't give us vocabulary for, so we are using the extinct process profile still, right? So
Not extinct.
The somewhat deprecated process profile is still being used in this context. So we, in addition to doing this work, as I mentioned, the social and behavioral sciences are waking up to the need to do this kind of work, this kind of representation and standardization, and as a result, we and others have been trying to build a community around this kind of work for social sciences research, and this, we called it the Behavioral and Social Sciences Ontology Foundry, in obvious direct analogy to the OBO Foundry, and you can join this mailing list and participate in this community. We haven't actually had any meetings or anything yet, but we will in the future, and try and help us to map out this landscape of the social world and behavioral research. Everybody who wanted to got a picture of that. Does it still work? It does. Excellent. So now I want to indulge in just a few thoughts about, just a very few thoughts about ontologies, AI, and the future. So one question I get asked really often these days is, why would anybody do this kind of hard work, right? It's really hard work, building ontologies. You work hard to try and come up with definitions and then to try and get your community to agree and so on. If we now have systems like ChatGPT, why do ontology work, right? And I think this is something which we as the ontology community ought to have good answers to. And those answers are not as obvious as whatever the previous generation of natural language processing models were, right? Because actually the tools are really able to do things that they were not able to do 2 years ago, 5 years ago, whatever. So I think that we are actually seeing a kind of technology shift in the way that we're going to interact with text and information and all of these things. And that's real. I don't think it's worth completely belittling, even though obviously language models are having many failures as well. But they really do things that could not be done before. And I think this will have broad-ranging impacts on some of the things that we had used ontologies to help with, such as better searching and so on. So using ontologies to support semantic search, maybe this will be less necessary when we have really good language models. However, in my view, having done this over a number of years, building consensus among a group of people or a community cannot be automated. And this is something which with Fabian we wrote a whole paper about, but it really bears saying over and over again. Ontology work is people work. It's about getting people to agree and figuring out what people sort of have in their minds when they cannot even represent that themselves in text. So you're sort of getting out of the people what they think the thing is, and then so that's the elucidation part, and then you're helping to negotiate between differences. And from this, I think you just cannot automate, because no matter how good a system is at working with text that is expressed well as text, these things that we argue about when we argue about all the things that I just showed a whole series of, they are not easily represented in text. You actually have to understand. You have to understand people, and then help people to agree on things and find common ground. And this work, I think, I don't see any chance that it goes away. In a way, it just gets more and more, right? We have more and more of a need to find common ground, to negotiate on common meanings. On the other hand, I do think there is a role for the new language and machine learning technologies in helping us to focus more on what is useful for us to do, which is this hard work of the community consensus negotiation, and focus less on kind of easy and boring and repetitive work. And for this reason, I think we should all embrace machine learning as a way to extend existing ontologies where the hard decisions about the upper level distinctions and so on have already been made. And together with Fabian and colleagues in Magdeburg, we have been working on this for chemistry. Chemistry is a particularly nice domain to work on this, because the representations that we talked about, the structural representations, have so much information in them that you can use to really train a neural network model to predict chemical class membership based on those structural representations. And this is not completely trivial. If it were completely trivial, you never would have needed a chemical ontology in the first place. It's not exactly encodable the classes that matter or the classes that don't matter. To chemistry has sometimes a historical reason, sometimes it's about the biological activity which you can't just see from looking at the molecule and so on. So what we did is we took the existing ontology, and from that we derived some training data, and then we trained a model, neural network model, and this was then able to predict class membership for new molecules which it has never seen before. And so you create this kind of cycle where your ontology can grow, but it grows from this core of distinctions which the ontology had learned, which the ontology had made manually by people working on the ontology. And then another really exciting sort of side effect of this work was that we were able to observe that this task, we trained this neural network to predict membership in ontology classes. This process we were able to use to improve a neural network to do another task, a kind of common task in chemical informatics, in modeling, which is predicting the toxicity of chemicals. So here you have a task which many people work on, and neural networks and all the kind of machine learning methods are used in order to solve this problem. You have some data sets which say which chemicals are toxic and which aren't. Typically you split up your data set and you train your model with half of it or 2/3 of it or 4/5 of it or whatever, and you try and predict the bit that you haven't seen. And what we did was we had two sort of comparisons. On the one hand, we did what would be a normal vanilla neural network. We trained it and then we applied it to the task. And on the other hand, we put a middle layer where we first taught the network about the ontology, so KEBI, We taught it to predict class membership in the ontology, and then we did the same toxicity training on this neural network. And what we saw, which you can see on the right-hand side, was that the neural network became better at predicting toxicity. It learned faster, and the results were ultimately better. So the blue line is consistently above the red line. And in particular, on the very right-hand side bottom, what you see there is a network which becomes worse over time. And what this shows is that the network has initially overfitted to the first examples that it was given, but with the ontology pre-training, it didn't do that. So it got better and better. So teaching the neural network the distinctions that chemists had made and put into an ontology helped it to learn faster with less data in a more generalizable way. Of course, this is just one experiment, and we hope that we will do many more experiments and be able to show this more robustly in different scenarios. But intuitively, it makes sense that somehow what we have captured in these ontologies are meaningful distinctions which are relevant, it's domain knowledge, and getting those meaningful distinctions into systems that are then able to do other tasks, it should help with the outcomes. I skip over this bit and get quickly to my summary. So, BFO is widely used. It's also abused. Werner's point yesterday, sometimes people use it without really trying to understand it, and it still has gaps that it would be good to fill. But overall, I must say, I think that it has a net, quite positive effect on ontology development across a very wide range of different domains, especially the core distinctions, dependent or independent, process or material entity. It's really bad when people get confused about those things and then build ontologies, right? Then you see really big messes. And it's much better when you start from at least a good understanding of those distinctions and then build your ontologies. I would like to see quite a lot of work in terms of how you represent processes, attributes of processes or something like that, patterns, and consistently domain experts dislike some of the terminology, such as the expression realizable entity or even the distinction continuant and occurrent. And it would be nice to see some sort of informal layer of domain-friendly terminology in addition, even if you keep the technical terms as well, like as the primary terms, but some sort of user-friendly layer of synonyms which people can relate to more might be helpful. And then finally, I do think that information technology is evolving, but the basic problem that ontologies have to solve is a human problem, and we still have to solve it.